It was a weird beginning, so during COVID time, not quite the best way to start a new job, but everything is online. It's been a real pleasure to work with you, Katie, and I just wanted to thank you here, and I wanted all of us to also thank Katie, and good luck.
Everybody for making the job fun.
I mean, it's been really wonderful. So, as you can see, Katie is due with twins. Anytime between now and
Hopefully not now, but
that's why when we had to evacuate earlier, we debated. Is it really reasonable to evacuate?
I would prefer not to.
All right, thanks again. Katie will be here on Wednesday or Thursday? Thursday. So if you want to stop by in a less professional context, we'll be here for lunch, 12 to 2 or something like that. So please, if you want to say one last time goodbye, stop and say goodbye to Katie. Thanks. All right, today it's my great pleasure to introduce Eleanor Knox, who is professor at King's College London. Before that, she was a Liverpool. I guess I'm not saying it's the right way, right?
Hey, you're fine.
I'm not sure it's not the right way. Early career fellow, she worked on the foundation of space-time physics, but she also has a broader interest in the philosophy of science, including the relation between theories and including the notion of emergence. So we've been very lucky. She's been a senior visiting fellow this year. That's the second time she's spending time in Pittsburgh, enjoying lovely weather. And it's always a pleasure to have Eleanor. She's really a wonderful member of philosophy communities. Today, Eleanor will be talking about, also, she's published in the best journal, I should say. Actually, I did check this morning, everything from news to BGPS to PPR to studies to philosophy of science. It's really an impressive list of publications. And today, Eleanor will be talking about functionalism in physics and inter-theoretic relations. The floor is yours.
Thank you very much, Edward. And yes, it's been a hugely fun semester, and I'm looking forward to the next one. And I also want to, I think Katie's run away. I was going to say, I want to say thank you to Katie for having made it me feel really welcome here and just made the centre a really fun place to be. All right, wonderful. So this talk may be really badly aimed at this audience. So this is a little bit more big picture than a lot of stuff I've done in my time, and it's also hugely centered on thoughts around about David Wallace's work, and David's not here. It's got to do with inter-theoretic relations, and Bob can't make it. But anyway, so it's maybe it's appropriate to give a little bit of prehistory of the talk. So this largely, I've been thinking about a view I call space-time functionalism for a long time, which grew out of very specific examples in the philosophy of space-time physics. So it didn't really grow out of the desire to be a functionalist about something. It grew out of a way about thinking about interpreting theories that was based on examples that then seemed very apt for the label functionalism. And then, of course, when you put a label on something, especially one that's got as long a history as the word functionalism, everyone wants to know exactly what you mean and how it fits into 1,000 debates. And I, with the help of David Wallace, have been trying to work that out for years, really. So in a sense, the view starts with how I think we should interpret theories and sort of ends up with what the connection to anything else in the literature is. And David has spent a long, so I don't think most of you will not have fallen into this terrible trap, but Oxford was rather a Lewisian place when I was there. And so lots of one's automatic clear references for things kind of were based in David Lewis when it came to kind of metaphysics and bits of philosophy of science. And David spent a long time talking me out of thinking that my view had anything to do with David Lewis. And we've sort of been talking for a while about potentially co-publishing a paper on how to think about functionalism more in his strain than Lewis's. And it's possible that this paper will end up being a joint paper with David, but unfortunately I'm too disorganized to have written it up and asked him whether he agrees with it. So it's either something you'll hate that he has nothing to do with, or partly joint work, and I have no idea which one. Okay, good. So here's the puzzle. So various views in the philosophy of physics appeal to functionalism about theoretical terms or concepts, but it's often a pretty hand-wavy thing to do. I'm a culprit in this. And very few people have said exactly what kind of functionalism best fits the needs of philosophy of physics. At the same time, lots of people have thought that functionalism has something to do with inter-theoretic relations. It's going to provide some kind of bridge between theoretical levels. And again, exactly the way in which it's going to do that has been pretty unclear in the literature. So what I'm going to do in this talk is talk about one option, which has the benefit of clarity and I think the disadvantage of potential inapplicability of thinking of functionalism as Lewisian reduction. I'll then go on to explain in broad strokes what I mean by something like Dennettian functionalism. I don't even know if Dennettian is the right word for it. My Dennett exegesis is poor and it's hard if you've ever tried to do Dennett exegesis. And maybe it should all be Wallacean functionalism, because really this is Dennett as interpreted by David Wallace. But anyway, so I'll go on to explain what I think that means, and then how it relates to David's maths-first structural realism, which he gave a talk on a few weeks back here. So hopefully that's not going to be a total blindside. And then I'm going to take all of that and try and apply it to an example, which I think John Norton's going to hate. So, you know, this is how we're just going to piss everyone off at once, of phase transitions, and say how I think that this broad framework can actually take away some of the heat and shed a little bit of light on why everyone gets in such a muddle about cases like phase transitions. And I think you're not muddled, I know. But that's why I don't think you'll like that bit, because you'll think we should never have been muddled in the first place. So why am I trying to unmuddle anyone? And then I'll draw some conclusions. All right. So the origins of this paper came in the fact that a couple of years ago, Jeremy Butterfield and Enrique Gomes wrote a paper basically saying that all of these people were using functionalism in the philosophy of physics literature, and they were all using it badly because they hadn't read their Lewis, and everyone should just be more Lewisian and we'd all be terribly clear about everything. They, for example, said that recent philosophical literature had failed to stress that functionalism was a species of reduction. It's this nice thing that uniquely defines a concept by its functional role and can simultaneously define several concepts, and it provides mandatory bridge laws, statements of identity that you then use in Hegelian reductions. So this is a wonderfully clear framework. And they're advocating that we adopt this clear framework rather than hopeless hand-waving about functionalism. So the process as they see it, when you provide a functional analysis of something, is you choose a theoretical term to functionalize. You do a lot of hard theoretical work picking out its functional role in relation to other terms, divide up the language into the terms you understand and the terms you want to functionalize. You're going to do a lot of actually quite scientific work in this if you're giving functional analysis. Then you're going to find the realizer of the functional role in a reducing theory, and the resulting statement of identity is going to be a Hegelian bridge law and provide a reductor. Good. So, I mean, I think I'll eventually have more concerns about this, I think. And I say in a sense, I entirely agree with Enrique and Jeremy that lots of people have been muddled and confused and unclear in the way that they use functionalism. I disagree with them that I think that this project of Lewisian functional reduction gets us very far in many interesting places in science. But two immediate concerns you might have is that the whole notion here of what you're doing in functional analysis looks very tied to like giving a Ramsey sentence and looking for a realizer in a Ramsey sentence. It looks like you're assuming a syntactic view of theories. We're assuming we can give a kind of predicate analysis of our theory. And it's not at all clear. I mean, not that they're saying it has to be, but a couple of the examples I'll look at in a second show this. It's not at all clear how it's going to relate to all of this stuff people have said about kind of interesting cases in physics where we get puzzled because we think something has a kind of novelty or emergent quality whilst being reducible. And some people have seemed to think that functionalism has something to do with number two. So I think part of the kind of view that they're being inspired by in order to criticize it is a view that took a thought that I think has something very right about it, which is that being a space-time functionalist, thinking that how you identify space-time structures and theories has something to do with their functional role, might be helpful in dissolving some of what you might think of as the puzzles of quantum gravity theories that don't have fundamental spacetimes. I think there's something right about that. But so Chris Woutrick and Vincent Lamb wrote a paper called Spacetime is as Spacetime Does, where they claimed that functionalism was going to be super crucial in understanding the emergence of spacetime. And they very explicitly did exactly what Jeremy and Enrique suggested they do, and used sort of Kim's Lewisian framework to do this. And they said what we ought to be doing when we're thinking about emergent spacetimes and quantum gravity is we ought to be thinking, we ought to be looking for something in the quantum gravitational theory that realizes the space-time role. That's basically, so we analyze space-time functioning, we look for something in the quantum gravitational theory. And when I first saw that paper, I was quite surprised that just wasn't the role that I thought functionalism would play here at all, because this is reduction. And they wanted to talk about emergent spacetimes, and it just seemed a little bit puzzling as to how we get a gloss on emergent spacetimes. So they they explicitly say, oh, Kim thinks of this as reduction, but we think of it as emergence. And pretty quickly, people glommed onto this and said, look, that's not going to work to give you anything, to give you what people say you're getting in emergent spacetime theories. If you assume a kind of realizer functionalism, whatever realizes the spacetime role just is spacetime. So if you found a realizer of the spacetime role in your quantum gravitational theory, you've found spacetime in your quantum gravitational theory. Far from kind of vindicating or explaining the possibility of an emergent spacetime theory or a fundamental theory that doesn't have spacetime in it, you've done the opposite. You've shown that your fundamental theories do have spacetime in them. And that didn't seem to be the project that Lamb and Woutrick had set out to do at all. So, for example, Nick Huggett and Chris Woutrick are writing a book on emergent spacetimes in different theories of quantum gravity at the moment. And part of the whole idea is meant to be that we're meant to be understanding theories that don't have spacetime in at the ground level. You might or might not think that's a good project, but that's the project. And functional reduction doesn't look like the right place to look to achieve that project. You only escape this kind of problem if the thing that realizes the spacetime role isn't in the fundamental theory. But then all the work is in explaining what the relationship is between the realizer of the space-time role and the theory. And I guess I sort of always thought that that's sort of roughly where the action was. It was, you kind of got, space-time functionalism helped you be very metaphysically laid back about space-time. And then you did some very hard theoretical work that I have no idea how to do, working out how spatiotemporal theories connect to quantum gravity theories. Okay. So that kind of leads to the question that's sort of made salient by this use of this functionalist reasoning. How should the functionalist accommodate the possibility of emergence? Where emergence here, I just mean something that's compatible with reduction, but that is a kind of interesting novelty. Features that we want to identify in a higher level theory that we want to say aren't there in the lower level theory. There's more to be said about that. But, so they could do two things, right? They could either say, well, I like the Lewisian framework, but what I'm really doing is I'm doing my Lewisian functional analysis at the level of the higher level theory, and I don't find the realizer in the lower level theory. I find some really complicated, highly idealized, emergent, approximative thing that realizes the role. And then a lot of the work, as I said, is in understanding how the lower level theory relates to that highly approximative, idealized, emergent thing. Or you could just say, David Lewis isn't very helpful here. He's not really getting us any further. And so then you might want to go back to where else this pesky word functionalism has cropped up in philosophy of physics. Certainly any good Oxford student, perhaps some other people, will have first encountered it actually in a philosophy of physics context when they have been indoctrinated heavily with the Everett interpretation. And so one of the first times I would have come across functionalism used outside the philosophy of mind literature would have been in David Wallace explaining how it is that you get from superpositions to multiplicity in an average interpretation of quantum mechanics, right? One putative problem for many worlds theory is that you say we have one particle in a superposition of states, but we want to not say we have one Schrodinger's cat in a superposition of states, we want to say we have multiplicity of cats, two cats. And he had to justify a kind of view of higher level ontology on which you had that kind of multiplicity, despite having, despite the fact that wasn't the gloss that you put on the fundamental physics. And Wallace's way of justifying that was to appeal to Daniel Dennett, which I'm sure some people found obscure, but he found very helpful. And I think that maybe by the end of this talk and the end of his talk last week, it'll start to be clear why he thinks it clarifies rather than obscures things. So Wallace thinks that classical structures are recovered from the quantum state by a kind of functionalist criteria. You just decide that a cat or a tiger, or maybe pick like Gene or something a little bit more scientific sounding, is just anything that can play a role in a particular science. So, you know, we decide there's a cat around when there's something, you know, obeying some laws of maybe zoology, biology, maybe folk theories of animal psychology. And that's the individuation criteria. And there's no further criteria about how it's based in the fundamental state. So if something behaves like a macro object of classical theory, it just is one. And he then associates that with Dennett's real patterns ontology, which again is something that lots of people find very, very confusing and obscure. I think David's recent work gets a little bit closer to understanding how you might flesh that out. God knows whether it's a way you might flesh it out that Dennett likes, but maybe, maybe we'll get closer to that today. All right. So how does that relate to, how does this slightly hand-wavy version of functionalism relate to the nice, precise, but potentially inapplicable Lewisian functionalism? Well, if you ask David, he's going to say something like, well, the Dennettian functionalist might be interested in finding out what instantiates the functional role, but that's not the point. They're not looking for a realizer. That's not the thing. What they're doing is kind of licensing a claim about what's going on in a theory, what's around. So, you know, the fact that there is a Gene or a tiger or a space-time is licensed by how stuff fits together in a theory and the fact that we do think that theory is instantiated out there in the world. So we know there's a realizer. We don't know what it is, and we're not necessarily engaged in the project of going out and looking for the realizer. And part of the objective of the functionalism is to be very liberal about what on earth might be the realizer of that role. You don't have any ideas about, you know, constitution or material nature of what realizes the role. The theory works, something plays that role in the theory, so that thing exists. So how do you flesh that out and make it precise in a way that might, well, this is where this talk is just an impossible attempt to satisfy many people, in a way that might be precise enough to satisfy Jeremy Butterfield, right? But nonetheless doesn't fall into this sort of inapplicability problem. Well, is this just Lewisian functionalism, but having announced that I don't care about the second step, the reductive step? And what on earth has it got to do with the real patterns ontology? And how does all the really good work, interesting work, that's grounded, unlike much of this talk, is grounded in real physical example that people have done on idealizations, limiting relations, and thinking about how things actually work in science, has any of this relate to all of that? Okay. Well, an awful lot here is really going to depend on having something like a broad metaphysical picture to fit this into. And for Wallace, that metaphysical picture is going to be inspired by the kind of original ontic structural realists, so in particular by Ladyman and Ross. But of course, none of this all fits together quite and makes sense, I think, until you start going down the road that David was pushing us on a few weeks ago, a version of ontic structural realism that has something in common with the kind of thing that James Ladyman's been pushing for a long time, but perhaps has some novel qualities. So how David thinks about ontic structural realism, maths first structural realism, is that we should think of theories semantically as classes of mathematical models. The purely there is in question. I'm going to come back to that because purely mathematical models don't necessarily make a whole lot of sense. And then the kinds of things that we could ramify, the kind of thing you could offer your Lewisian analysis of, are going to be what he calls predicate precisifications of those mathematical models. Our attempts to linguistically capture what's going on in the mathematics. For him, that second thing, the predicate precisification, the kind of syntactic, ordinary language, set of statements about what's actually going on in the theory, that object, that kind of syntactically thought of theory, is heavily underdetermined. It's not even truth apt in the stronger version of his view. They go way beyond the content of the theory itself. So a commitment to the content should be a commitment to the representational capacities of the mathematical models, and not to all the stuff we'd like to say about mathematical models. So maths first structural realism is not committed to the truth of what he calls the predicate precisification. Maybe I should find a better word for that, because I'm going to say predicate precisification 10 more times in this talk. And again, if you want to kind of throw a bagel at me by the end, I'll be sympathetic. Good. So on this picture now, what happens to inter-theoretic relations? Relationships between theories are understood via mathematical relations between mathematical models. So we don't try and understand the sense in which Newtonian gravitational theory is approximately true. We understand the representational capacities of Newtonian gravitational theory by understanding its relation to general relativity. And models of general relativity can approximately instantiate models of Newtonian gravitational theory, and we understand everything we need to understand about the applicability in the domain of Newtonian gravitational theory and how we can use it when we understand those relations. Now, where does this Dennettian real pattern stuff come into this? Well, here's what Wallace's paper has to say about it. He says the version of maths first, I can't say math first, I'm too British. Ontic structural realism I give here offers a possible analysis of what we might mean by a real pattern. If you have two ontologies, X and Y, X consists of real patterns in Y, if and only if there are two theories, Tx and Ty, such that Ty instantiates Tx, and X, Y, and Y are respectively the best predicate precisifications of Tx and Ty. But for Wallace, constructing ontologies X and Y, that's the thing you do when you give predicate precisification. It's pragmatic, overwhelmingly. So the dose of pragmatism is taken in the construction of the respective ontologies from the theories, but the instantiation of Tx by Ty lacks a pragmatic component. So you're kind of a realist about the mathematical models, but more of a pragmatist about the ontology. So here's the picture he prefers. He goes through a bunch in his paper, but this is his preferred picture. It's one where you have a very well understood relation between low-level theory and high-level theory in the sense of mathematical models. And you then get a lower-level ontology from the lower-level theory and a higher-level ontology from the higher-level theory. But it needn't follow that there's any particularly neat relationship between the lower-level ontology and the higher-level ontology. Both of these are undetermined processes with a pragmatic component. You come up with your kind of interpretation based on a whole load of considerations we're used to. But it doesn't mean that, some, mereological composition of the objects down here has anything to do with the objects up there. And he thinks what a real pattern is just the word for the thing in the lower level ontology, whatever that thing is, however complicatedly structured that thing is, that we think instantiates the higher level ontology. So to say that objects are real patterns in the lower level ontology is basically just to assert that this relationship exists. So this has the benefit, I think a lot of people have found the real pattern talk pretty obscure. I think this has the benefit of at least making it clear under what circumstances you might apply it. So where does functionalism fit in that picture? So I think how Wallace thinks of it is that the Dennettian functionalist thinks your interpretive claims are licensed by functionalism. So when you say there's a cat in my theory, there's a particle in my theory, there's a space-time in my theory, part of what you're saying is the maths is behaving in such a way that I think there's something that fits this particular kind of role. Now, of course, once you come up with your best predicate precisification, ramsify away if you want to, feel free. But you're not generically going to expect to get an interesting reduction from that. You're not going to find a realizer of the role of X, of a role of X in the ontology of Y. Or you might sometimes, but you won't generically. The action and the thing that we should be realist about and the real relation holds between the models of Tx and Ty, not between the predicate precisifications and the ontologies. So I think this gives us a possible picture of how to think in very broad strokes about some things that happen in philosophy of physics. So I think if you think of model reduction as a relationship between mathematical models, and Hegelian and functional reduction as a relationship between predicate precisifications, then you can think of this thing that a lot of philosophers of physics want to call emergence as a relationship between predicate precisifications. Emergence is going to happen in the presence of reduction just when we understand the relationship between mathematical models perfectly well. But we don't have an Hegelian or functional reduction at the level of the linguistic precisification. And it might be that certain relations between mathematical models that we've been really interested in, like taking infinite limits or particular kinds of idealizations, are going to be particular good indicators that that this Hegelian reduction is going to fail. Okay, so this is the closest I'm going to get to real physics. Let's apply this to an example in the philosophy of physics literature that's had an awful lot of airtime, right? A putatively puzzling inter-theoretic relation, which is for the phase transition from liquid to gas for a single kind of system at less than critical temperature. It's just to be a little bit specific. So in thermodynamics, we say that phase transitions involve a non-analyticity, a discontinuous kink, right, in the free energy of the system. And thermodynamics has a perfectly well understood expression for free energy. We understand it perfectly well in terms of thermodynamic variables. So within the context of thermodynamics, this is a very powerful, useful description that we understand how to use perfectly well. We also have statistical mechanics, which is an incredibly unusual science because it was designed to provide a reduction. We don't very often do this, right? But the whole point of StatMech was that it was supposed to be the reductive base for thermodynamics. So it's really weird if you don't think we can reduce thermodynamics statistical mechanics, because this is sort of what this was designed to do. But we have an expression for the free energy in statistical mechanics. We express it in terms of the partition function. And I mean, these details don't particularly matter for the point at hand, but so the partition function basically tells you something about the probability of finding a system at temperature T in some given energy microstate. But then you have a puzzle, because the partition function is an analytic function, the free energy is an analytic function, and analytic functions aren't non-analytic, right? They're infinitely differentiable. They can't have discontinuities in their derivatives. So the very reductive base for the statistical mechanical phase transition, I mean, you can get into, there's lots of complexity about what kind of phase transition we're using. There's much skill think on this, but this is the very basic puzzle. So we have a puzzle because it looks like you just can't have a thermodynamic phase transition in a StatMech system. But physicists are nice and imaginative and they saw how to get around this problem, and they say, look, you just take the thermodynamic limit. We just take n, which might in some cases represent the number of particles, off to infinity. And then we point out that the n goes to infinity limit of the partition function can have non-elasticities, and that's how we find the phase transitions to identify with the thermodynamic phase transitions. Okay. So what we have here is, I mean, clearly something that can have, there's a lot of questions about how one really understands the relationships with models, the role of the Ising model, etc. But what you have at its heart here is a tension between two thoughts. One is, I found out what a phase transition was in thermodynamics. I'm conceiving of it as a non-analyticity in the free energy, and there's no such thing in statistical mechanics. So it's a kind of reductive failure. On the other hand, it's just insane to say there's a reductive failure here, because if we understand anything in inter-theoretic relations, we understand this. I mean, this is like undergrad textbook level StatMech. I mean, we really understand very well the relationship between the free energy in thermodynamics and the free energy in statistical mechanics. We have perfect mathematical derivations of it and loads of models to justify them, and a huge amount of understanding. So it's extremely strange to think that you have some kind of failure of reduction in this case. So that leads some people in the literature to see this as a kind of example of this kind of generic phenomenon we have in lots of bits of physics, where there seems to be something novel going on that we might want to tack the label emergent onto. But we also have a perfectly decent reduction, not particularly necessarily in the Hegelian sense, but a perfectly good reduction in the physicist's working sense of we understand how these two different theories can model this system extremely well, and we understand the relationships between models. And when I poked into this, I realized that someone's actually analyzed this as a failure to find a suitable realizer in a functional reduction. So Soren Bangu thinks what's going on here is that you functionalize the property of undergoing a phase transition. So you say, it's a definitional claim, to be a phase transition is to be undergoing a phase transition is to have a non-elasticity in your free energy. Whether that's good functional analysis or not, I'm not 100% sure. And of course, what you discover is there's no realizer of that role of statistical mechanics. Well, what should the Lewisians say about this example? Well, there's lots they can say, and I think there's a certain sense in which a lot of the literature on this fits into that Lewisian paradigm. You end up saying a whole load about what the realizer really is. So maybe you say, okay, but the thing that realizes the phase transition role is the Z in the infinite limit, and and there's an enormous amount of ink spilt on what we mean by phase transition, and whether either you mean something by phase transition that means they don't happen in real systems, or you mean something by phase transition that means that statistical mechanics doesn't describe them, or you pick your position. But a lot of them fit into this kind of thought of, well, what we really need to do is understand what it is that's realizing that thermodynamic phase transition role, and it's going to be some idealization of the stat mech, an emergent thing itself. But the very fact that people still talk about this, I think, shows that perhaps some kind of, people feel there's some unresolved mystery when you give that kind of analysis. And I think if we separate out understanding relationships between mathematical models and our linguistic precisification of those mathematical models and all the interpretive stuff we do, and this thing that we have to do, that we're obliged to do, both we as philosophers of science, but also physicists have to do, we have to put linguistic glosses on what we're doing. But if we see that process as a kind of secondary process, I think some of the air of mystery is dissolved. So in Wallace's picture, we understand the relationship between thermodynamics and statistical mechanics by understanding how models of statistical mechanics instantiate models of thermodynamics under appropriate conditions. When you talk about the IT model, when you talk about thermodynamic limits, that's what you're doing, you're understanding model instantiation. Mathematical limits aren't mysterious at all. They're just a crucial part of how you understand how one model instantiates another model. Wallace, it's going to be typically part of, when we understand the relationship between general relativity and Newtonian gravitation, these limits pop up all over the place. There might be lots of work to be done in particular cases and in more complex cases in understanding how we apply these kinds of model relationships. And that's the correct domain of kind of worrying about theory relations. But the work here is all in the mathematics. There isn't substantive work to be done in having an argument over the definition of the words phase transition. So what do you think is going on with the word phase transition? Well, our best predicate precisification of thermodynamics says things like phase transitions occur when there's non-elasticity in the free energy. And that's not realized in statistical mechanics. But nonetheless, we have a good understanding of the relationship between the two theories. So what we have is a failure of phase transitions to be functionally reducible, but a perfectly good reduction in this kind of model theoretic sense. And I think that potentially gives you a sense of what people mean when they say something like this, phase transitions emergent. There's a kind of linguistic mismatch, but not a mathematical one. I mean, am I trampling here all over? There's an awful lot of work on phase transitions, right? And there's some really nice work. So Patricia Palacios has some really nice work putting into a more Hegelian framework. But it's interesting that I think some of the good work on this, I think Patricia's is an example, says that in order to reduce phase transitions, you have to do a kind of two-step reduction. You do a Hegelian reduction in terms of logical derivability, and then you do a second thing, which doesn't fit into the Hegelian framework, which is mathematical derivation. And it's interesting that you have that two-step analysis, I think, because it kind of shows that there's something right in separating out this good mathematical understanding we have from the attempts to do something like an Hegelian reduction. What else might one worry about? Well, one thing that I am genuinely worried about, and I haven't in David's framework, and I haven't worked out sort of how to, I don't know where he sits on it, and I don't know, and I don't know how exactly to draw the line, is in the division between these sort of linguistic precisifications and his mathematical models. So one thing, the first thing that you might want to point out is that the functional role for phase transitions, I mean, if that's what I mean by functional role for phase transitions occur whenever there's non-analyticity in the free energy. That sounds awfully mathematical. Although, of course, it's certainly true that if you're going to think of having a kind of complete predicate precisification of a theory, it's going to involve mathematical predicates. It's also true on the other side that Wallace's mathematical models can't be purely mathematical, because uninterpreted maths isn't going to have the representational capacities he wants it to have. So there's got to be more to this sort of model. Sort of, I feel that there's enormous value in driving apart this activity that we perform of kind of putting a linguistic gloss on our mathematical models and the mathematical model, but it's also very hard to know whether we can really disentangle those two things and how completely we can. And I'm very unsure about whether the line that I'm drawing here is one that Wallace would like. So sometimes he talks as if, this is where it's kind of ridiculous figuring this out, David in the room, but it's not like he's not across the road and I haven't had plenty of time to talk to him. But sometimes David talks as if the only thing in this predicate precisification is like things that, you know, good philosophers of physics would barely waste their time on. Right? The only things over in this interpretive work are like, you know, what are the objects and what are the properties? You know, are particles charged or is charge particularized? And if that's all there is to this sort of underdetermined linguistic stuff, then most of what we do as philosophers of physics, and indeed physicists do when they interpret their theories, is way over on the mathematical model side. And what I'm suggesting here is that I'm not sure that's the helpful way to think about things. I think an awful lot of the interpretive work we do has to be thought of as over on this kind of linguistic-y predicate precisification side. So if you're going to pack even, is there a phase transition happening? Answers to questions like that into the predicate precisification, that's going to draw the line of what sits over here in the predicate precisification much further over than I think Wallace has in the past. And it's not clear to me that you can make the distinction cleanly, and whether you can be content with a messy distinction. At the same time, it seems to me that there's something completely right about the fact that a great many of the messes we get ourselves into in philosophy of physics come about because we're trying to work out how to attach ordinary language or even theoretical language terms to our mathematical models. And so you know, so the distinction seems helpful, even though it can't be made cleanly, but I don't know how much of this work it can do if it can't be made cleanly. Okay. So just recapping what all this might have to do with what kind of functionalists we should be. Dennettian, Wallacean functionalist uses their functionalism to license interpretations of your mathematical models. And that makes sense in this Wallace picture, right? Because what else could you be doing? When you say there's a particle or a space-time or even a phase transition, you're not saying something deeply true about the nature of the fabric of the universe. Nonetheless, you want to constrain your language somehow. And so functionalism is a very helpful way to constrain your language. You know, to say there's a particle somewhere is to say that there's some structure in the theory that's behaving in a certain kind of way. Or indeed, to say that there's a space-time in your theory is to say that there's something that's behaving in a certain kind of way. That there's something in the theory that fits together with the other pieces of the theory in a particular way. It's underdetermined how you do that process, but it doesn't float completely free of anything. I mean, you'll do an awful lot of violence to your assumption about the theories if you take these terms completely free of their normal associations. So you justify your particular predicate precisification, this quite important process of interpreting theory based on effectively functionalist grounds. They're not true, or even approximately true, these predicate precisifications, but they are pragmatically constrained. And they can be highly pragmatically constrained. So one of the reasons that I've always thought it was important to think about what you meant by the term space-time was because I'd watched physicists get muddled by getting it wrong. And space-time in particular is a really important term because it has some automatic empirical associations. Right? People think that it's going to have something to do with what your clocks do, and what rulers do, and what certain kinds of physical systems do. They're going to make a bunch of assumptions about how you could construct tests of your theories based on what you've identified as your space-time structure, or how real systems should behave. So it's not that the pragmatics here aren't highly constraining. It's not that you can just do whatever you like, and it's not that this project of interpretation isn't important. Some of these terms are going to help the models to make empirical contact. And, you know, I think it's a pretty good sanity check on your use of the word phase transition, that you think boiling kettles are undergoing a phase transition. In a sense, it's a pragmatic choice, but it seems like a very poor pragmatic choice to disconnect the word phase transition from a real kettle boiling. What's the role for Lewisian functionalism? Well, it may be that in some cases, you know, and I think, and yeah, this is the kind of thing, you know, maybe temperature and ideal gases, for example. In some restricted cases, it may be that you have a neat relationship between these linguistic precisifications at different levels. And it may be that you would gain some understanding by thinking you understand the relationship between them. But I don't think that's going to be the generic case or something we should expect. And so I think there's a very restricted role for thinking that there's an interesting role for Lewisian functionalism. And my hypothesis about inter-theoretic relations more generally is that a lot of the phenomena that have taken on the label of emergent in the philosophy of physics literature are those for which this, what I'm calling a simple Nagel-Lewis reductionism fails, because one of the problems with Hegelian reduction is that you pack enough into the bridge, you pack 5 pages of maths into a bridge law, then you can do almost anything with the Hegelian reduction. But a lot of things that people have thought were puzzling, a lot of places where people have thought that you know, the use of infinite limits, etc., have kind of betokened something in the higher level that wasn't there in the lower level, are cases where it's this simple predicate precisification, Lewisian reduction that's failing, but the reduction understood mathematically is proceeding perfectly well. And that's it. Thank you very much.
We'll take a 5-minute break and then we'll go in for questions. Yeah.
Check to get you something. All right, thank you. I already have my notes. Or not. I have a recollection.